In this video, we'll talk about the properties of fluids. And one thing we will define the first is the definition of pressure. Now, in Newtonian mechanics, when we study an object's motion, we said that force is important. Force introduces acceleration of an object. Okay, but now for fluids, we're going to think about pressure. Pressure is defined as force divided by area. Now here's an example. So let's say there's an area, this object here, and the upper surface area, let's say it's A. And if we apply a force F on such a surface, and F is not applied on a point, it's applied on the whole surface. Okay, so imagine there's a surface here, and then everywhere the force add up to be this value F. Then we define the pressure on the surface as, the symbol is P, as force per unit area. And the SI unit is Pascal for pressure. Now, once we define this pressure concept, then we think about the for fluids. Let's say there's a container and there's some liquid inside. Now, if you measure the pressure at every point of the inside the liquid, there should be some value of P. So let's say this point 1, we have P1, point 2, we have P2, point 3, we have P3, etc. And this pressure, we'll talk about the reason of this pressure is due to gravity. But the pressure is acting on everywhere in any direction, not just inside the liquid, but also on the surface of the liquid. So let's say if we think about the bottom here, the bottom surface here also experience pressure, P at the bottom, due to the liquid. And not only the bottom, but also the side wall. The side wall here also experience pressure on the side. And they have different values, okay? But the point is that the pressure is everywhere. And again, the reason for that is because of the gravity. So now think about the air in particular. So you know, on the Earth's surface, here's a schematic diagram. So let's say here's the Earth. Now we single out its atmosphere as a different object from the Earth. So it exists surrounding the Earth's surface. And if I think about, let's say, just one column, really thin column of such an air, then all the air particles inside the column experience gravity, mg, is acting on the on these air particles, and that's why they're going to apply pressure on each other. And the lower the altitude for the air column, so let's draw the air column diagram. The lower the altitude, let's say we're thinking about air particles here, then experience more pressure or more weight from all the air above this point. So particles here experience a bigger pressure than air particle here. Let's call this P1 and P2. Then we have P1 greater than P2. Okay, and reason for that is because the all these air particles, they stack up, and one sitting on the other, the higher one sitting on lower ones, and that is the reason we have a larger pressure as we go down. They also make a difference on the density. So now previously we have pressure change, and for density here, okay, the air particles are more compressed at a lower altitude. So the lower we go to, then the higher the density. Let's call this rho 1, the density at the bottom, and rho 2, density at the top. Then rho 1 is greater than rho 2. Okay. That's because the air particles are compressed together, okay, compressed more together at the bottom due to the gravity. So that's why we have, let's say, on the Earth's surface. So here's the Earth's surface. So on the Earth's surface, we call that right at the surface here, we call the pressure here sea level pressure. And this pressure is the highest of all the airs near the Earth's surface. And we have a value called the standard atmosphere pressure. And the value here is, let's call it P naught, is 1.01 times 10 to the 5th Pascal. And this value of pressure is then defined as 1 atm, 1 atmosphere. Okay. And in the future calculation, we're going to use this 1 atm to do a lot of calculations, because all the liquids that we're going to consider, they're sitting on the Earth's surface. So they experience this pressure at the surface. Okay, so let's say this liquid here on the Earth's surface, it experiences P naught right at the surface of the liquid. Okay, so think about inside the liquid. What kind of pressure we can write down? I told you earlier that the P1, P2, P3, etc., they're all different. Now, can we get an expression for all these P's inside liquid? Okay, so here's the diagram. So again, we have a container, and there's some liquid inside. The liquid density is low. Is rho. And we know at the surface of this liquid, there's 1 atm pressure, so let's call it P naught. One atmosphere. And when I think about a point here, let's say a d distance away, vertical distance away from the top, then what's the pressure here? Okay, so we know the reason we get pressure is because of particles stack on each other and adding their weight to the force or the pressure at the bottom. So the top atoms, top molecules, they will add that weight to generate some additional pressure, right, at let's say this point, due to the liquid here. So that's why the pressure at this point is given by P naught, the atmosphere pressure, plus this liquid column, the pressure due to this liquid column, and it turns out to be rho g times d. Okay, so we can actually figure that out. So let me draw a liquid column here. And let's simplify our structure. Let's say the top surface is like a sphere, like a circle. And it experiences force, let's call this F top. Okay, now bottom here also experience a force F bottom pointing upward, and then the area here is A, and also A here, the area. Now the height here is D. Okay, so now if I think about the free body diagram for this liquid column, now experience force from top, from bottom, and also gravity. Let's call it mg. And these three forces must balance each other, meaning the downward force, they're balanced by the upward force. So F bottom equals F top plus gravity acting on the liquid. Now F bottom is, according to this diagram here, is the 1 atm pressure times area A, and then equals, here is with the left side is bottom, so we have pressure P here, like in this diagram here. So start P naught is P, and at the top is P naught times A plus gravity. Now gravity is the mass here. I'm going to replace it by the liquid density times liquid volume. Right, the volume here is given by A times D. So that gives us this column, the volume of this liquid column, and then times G. Okay, so now all the A's cancel out. So that's why we get this relation: the pressure at the bottom equals the surface pressure plus rho GD. Okay, so that's this equation here, and this equation is called hydrostatic pressure. Hydrostatic pressure. So now with this pressure formula, we can calculate at any point, as long as we know its distance to the top, to the surface, then we can calculate its pressure. Now for pressure, for the measurement of pressure, we can use a device called a pressure gauge. And when we use pressure gauge, we need to be careful that it measures pressure difference. So it measures pressure difference. So let's say you use this pressure gauge at the near the Earth's surface, then the difference, the reading here, the pressure gauge reading, is given by the actual pressure of the liquid or the gas minus P naught. Okay, so it's actually a difference between the real pressure and the 1 atm pressure. So something I want to mention about the pressure gauge. All right, so let's talk about a principle called Pascal's principle. So we know Pascal did a lot of contribution to the liquid liquid property study. So that's why we named the pressure after him. So here is Pascal's principle. And it says that the change of pressure at one point in an incompressible liquid is the same as that at any point in the liquid. So first we need to have the condition here, incompressible liquid. Okay, if the liquid volume can change, then we don't have this Pascal's principle. Okay, so for incompressible liquid, let's look at again some kind of picture here. So let's say we have a liquid that go up to this level, and now if we apply, so at the beginning, let's say there's this 1 atm pressure, right, due to the air on the Earth's surface, right, 1 atm. If we apply, now let's put on a piston here, and then we apply some additional force on it. Okay, so now the pressure on the liquid surface is increased by this amount of F divided by, let's say, area A here. Okay, so that's delta P equals F over A on the surface. So in addition to P naught here, we have P naught plus F over A, the new pressure on the surface. Then every point inside the liquid, let's say point 1, point 2, now P1, okay, now it changes to the original P1, the new one I call the P1 prime, the original P1 plus delta P. So we have this force F divided by A, we can calculate for the change of pressure at the surface, and that also happened to the inside of the liquid. And the point 2 is the same. So we're going to say this principle says that delta P1 equals delta P2 equals delta P3 equals delta Pn. Okay, any point inside the liquid, they should have the same change of the pressure. Pascal's principle is also responsible for a device called hydraulic lift. Which is an important device to lift up a heavy object with a small force. Okay, so now let's see. Here is the look of the device. So there's this container, a specially designed container that looks like this. So on the left side, there's this narrow tube, and on the right side, there's a wide tube. And it's sealed, meaning let's say on the left side there's a piston here. Right side there's also a piston. Actually, let's draw a deeper container like this. Now let's liquid inside. Which is incompressible. Now at the beginning, let's say we do not apply a force here, we do not put that object there, then the pressure acting on the surface, both surface, atmosphere pressure, P naught. Let's also say that the area of this nanotube is A1, area here is A2. Now, right now they're at the same level, right? That's because they do not experience any external additional pressures on the surface. So they must be equal here at equal height. Now let's say we apply an additional force on the left side. Let's call it F1. And then we also put an object, a heavy object on the right side, area A2. And that object will generate a normal force acting on A2. And let's call that force F2. So that's the additional force added to the surface of A2. Now with that, the left side piston will go down to this new position, okay, because of F1. Due to this additional F1, it will go down here. And then because this liquid is incompressible, so that's why the right side must rise to a new height. And then the force acting on the surface here again is P naught plus F2. Okay, and here is P naught plus F1. Okay, so now let's think about the pressure relation at a certain level. So let me draw a line here, a horizontal line across the two tubes. And the thing about this point, the pressure at this point is equal to, according to the hydrostatic pressure formula, so P equals P naught plus F2 over A2 plus rho GH. Okay, so H is this height here. Oops. Let's hide H. So from the point that we want to, from the left tube's piston position to the right piston's position, their height difference, we call that H. So that gives us some additional pressure due to this liquid column. Okay, and on the other hand, we can also think about the left side. So the pressure here is equal to the pressure right at the bottom of this piston, which is given by P naught plus F1 over A1. And let's combine these two equations, and then we get the following equation. The two P naught cancel out, and then we can also rewrite the equation here for F2. So if I solve for F2, then F2 equals A2 over A1 times F1 minus rho GH times A2. So we multiply A2 everywhere, so that's why the last term here also get A2. Now usually we have A2 far greater than A1. Okay, so the area of A2 is much greater than the area of A1. And that would mean that we can use a small force F1 to generate a large force F2 due to this A2 over A1 large coefficient for F1. Okay, so that's the mechanism for the hydraulic lift that people use to lift up heavy objects. Okay, so now let's talk about buoyancy. And so what is that? The definition is the following. So an object in a fluid experiences a pressure difference from top and bottom. Now this pressure difference will produce a net force in the upward direction. And such a force is called buoyant force. Now here's the diagram. Let's say there's this container that has some liquid inside. The liquid has density rho. Now we put an object inside. Let's say it's a rectangular cube, and it has some area that look like this. Surface area is A. Okay. So now let's say there's a force acting on the top, and there's a force acting on the bottom. As we defined earlier, the difference between these two forces give us a net force pointing upward. And that's the force we call buoyant force. So let's figure out a formula for this. So now let's say we know also this height of the rectangular cube is h. Okay, let's call it h. Now we know F top is given by P top times A. Now F bottom is given by P bottom times A. And that's a relation between the top and bottom because of this height h. Okay, so the bottom here equals top plus rho, the liquid density times g times h. Okay, so that's the height difference h. So that's why the bottom here has a bigger pressure than the top, and then we multiply A there. So the difference in the force, which is defined as the buoyant force, is then given by this expression minus the top force expression, and then P top cancel out times A cancel out, so that gives us rho g h times A, and h times A is the volume. Okay, so V here is volume of the object. So that's why there's a net upward force equals the liquid density. So remember, here is liquid density, not the density of the object. Okay, and then times the gravitational constant g, and then times the volume of the object. That gives us the buoyant force. Okay, so now with this buoyant force, think about whether an object, what's the condition for an object to float or to sink. So now let me single out this object here, and then simply just draw a free body diagram using the F buoyant and gravity is in the downward direction. So now think about which one is bigger, the gravity or the buoyant force. And that comparison will determine whether the object can float or sink. And the M here is the mass of the object. So we can rewrite it as rho object times g times v. V is the volume of the object. And F buoyant we already know is rho liquid times g times v. Okay, so now if rho liquid is greater than rho object, so if the density of the liquid is greater than the density of the object, then the object is going to float. And if rho liquid is less than rho object, then gravity is going to be greater than the buoyant force. So that's why the object is going to sink. Okay, so now to summarize it totally, the relative magnitude of the liquid and also the object's density will determine whether the object can float or sink. Okay, of course we have also one more situation. If the liquid density equals object density, then the object is going to be in equilibrium, so it can stay anywhere in the liquid. And it's also called the Archimedes principle. The formula that we have here, rho g times v, give us the buoyant force. So that is also called the Archimedes principle. All right. So now lastly, we're going to talk about liquid flow. So now let's say in a tube filled with liquid, and we're looking at some cross-sectional area. The area size is A. So now let's say in unit time per second, we're counting the volume of liquid that goes through this cross-sectional area. We're going to count how much liquid goes through this area here in 1 second, and that is called the liquid flow rate. Let's use a symbol R to represent that. And the flow rate is defined as the volume, right? So that's why we call it RV. Now our purpose is to get an expression for this RV. And that's why we need the flow speed. So V here is the liquid flow speed. Means that in 1 second, the liquid is going to move V distance. So that's why the liquid inside this shaded volume can go through this area A. And that volume is given by V times A. Okay. And so that's why the liquid flow rate is defined as the speed, the liquid flow speed times the area A. And according to the liquid flow rate, we can actually define equation of continuity. And it says that the liquid flow rate at one region equals liquid flow rate at any region. So let's call that 2. And here's the diagram to show you that. Let's say we have different cross-sectional area for a tube. So it goes from this area A1 to some smaller area. So the tube now becomes narrower. And then we have this new area A2 for the tube, and liquid flow rate is flow speed is V1 and is V2 at second position. Then we have, according to this equation of continuity, V1 times A1 equals V2 times A2. Okay, and the reason behind this equation is the incompressible liquid. Which means that the volume is a constant, so it doesn't change. So the liquid volume doesn't change. So that's why we must have this equation of continuity for the relation between the two speed in the two area. Now, according to the equation of continuity, so now we can do some discussion here. So let's say, now according to our picture here, let's say we have A1 greater than A2. Then, according to this equation, we must have V1 less than V2. So the speed of the liquid increases. Speed increases as the cross-sectional area A decreases. Okay, smaller cross-sectional area will mean a higher speed for the liquid. Okay, now using this flow rate equation of continuity, we can also derive an important equation called Bernoulli's equation. And Bernoulli's equation is actually about the work, kinetic energy theorem. So let me set up the question, the system, so that we can talk about how to apply this work energy theorem for liquid. So I'm going to use a similar diagram as before. So let's this larger tube and then narrows to a smaller tube that has cross-sectional area A1 and then cross-sectional area A2 in a narrower tube. And we also have the speed of liquid V1 and V2. Okay, so now think about how to calculate the work done on the liquid. How can I calculate that? Okay, so now let's say we're calculating the work done on the liquid in 1 second per second. Okay, so now let's look at the larger tube here. So the left side, that's going to be a force F1 pushing the liquid, and liquid is going to move in 1 second this distance under the force, distance V1 times 1 times 1 second. So that's the distance moved under such a force F1. And on the right side, for the narrower tube, there's a similar displacement, and this displacement is V2 times 1 second under the force F2. Okay, now F2 is going to be pointing to the left side, right? Because it's going to applied on the liquid, which is at the center from the right side of the liquid, and that's F2. So the work done by these two forces are F1 times V1 times 1, and this work is positive. Now the work done by F2 is negative, so minus F2 times V2 times 1. Okay, but that's not all, because we also have the work done by gravity. Now in our picture here, we do not have that difference in the height of the liquid. But now let's say we have some kind of structure so that the height of the liquid right now along this direction, along this y-axis, which is vertical, changes from y1 to y2. Okay, so the work done by gravity will be negative mg y2 minus y1. Okay, now m here, what's m? M is this amount of mass, or that amount of mass that is being pushed, that changes its height from y1 to y2. So that's why m here is v1 times a1 or v2 times a2. And according to the equation of continuity, we know these two are equal. So an equal amount of mass displaced from position 1 to position 2. So that's why the work done by gravity is this equation here. Okay, so we need to add the gravity's work to the net work. So I talk about net work or total work done on the liquid. So equals minus mg y1 minus y2. Okay, now that according to work and kinetic energy theorem equals the change of the kinetic energy. So we're going to have 1/2 m v2 squared minus v1 squared to represent the change of the kinetic energy of the system. So now let's move all the terms contain 1, index 1 to one side, and all the terms contain index 2 to the right side, to the other side. So we get f1 v1 plus mg y1 plus 1/2 m v1 squared equals f2 v2 plus mg y2 plus 1/2 m v2 squared. Okay, so let's move. Let's do some replacements here. So P1 is the pressure P1 here times A1. So it's P1 times A1 times V1 plus M is V1 A1. So let's also replace it by V1 A1 times rho. Rho is the density of the liquid, and then Gy1 plus 1/2 m, again replaced by V1 A1 times rho, and then times V1 squared. Okay, so that equals the right side, P2 A2 V2 plus V2 A2 rho Gy2 plus 1/2 V2 A2 rho V2 squared. So we do some similar replacement here. Now use the continuity equation, so we can cancel out A1 V1 A2 V2 V1 A1 A2 V2 A2. We do this cancellation everywhere. Then we get to the Bernoulli's equation. It says that P1 plus 1/2 rho V1 squared plus rho Gy1 equals P2 plus 1/2 rho V2 squared plus rho Gy2. Okay, or in another word, we can say P, the pressure, plus 1/2 rho V squared plus rho Gy equals a constant. So that's called the Bernoulli's equation. Okay, so that's all for this video. Thanks for watching.